where we were left off with that last problem with the tree. So what did we have? We said every tree with V vertices must have V minus 1 edges. That's exactly the last thing we did Tuesday in class. And our proof was by induction. We are saying if this is my statement for V, this whole thing, I'm going to call this statement of V. The statement is the logical proposition I'm trying to prove. If a tree has V vertices, it must have V minus 1 edges. My proof by induction, the induction step, is that statement of V implies statement of V plus 1, right? That's, if you guys remember from Tuesday, that was our idea. So what did we say Tuesday? We said, okay, how do we prove this induction step? If T is a tree with V plus 1 vertices, so induction step, it's always an implication from something that I had at V or at N or yesterday to something that I want today. It's from N to N plus 1. It's from yesterday to today. It's never this is true or separately this is true. It's always an implication. If you can prove this problem for 20, you can also prove it for 21. If you can do something for this class, you can do something for the next class, so on and so forth. All induction steps are always of this flavor. So in here we say if this statement is true for any tree with V vertices, then we're going to prove it's true for a tree with V plus 1 vertices. So the first thing we have, like with any induction proof, is how do we relate this part with this part? This tree with V plus 1 vertices, can I somehow relate it with a tree with V vertices? This is always going to happen in induction proofs. Before you move on, before you start writing the proof, if you have a sum, sometimes the sum of the first n elements is something. Then you need sum of the first n plus 1 elements is something else. Your first problem is how do I relate the two sums? In here, we don't have two sums, we have two trees. So if I have a tree with V plus 1 vertices, I need to make this something that is a tree, call it not T, but a new tree, T prime, with V vertices, and something else. Presumably, I can't just say that tree is just a tree with V vertices. That won't be true. So I have this initial problem of how do I relate my new tree, the ones I'm trying to prove. This is called conclusion, right? And this is called premise. How do I relate the object in the conclusion, the tree plus V plus 1 vertices, with the old tree? And we did this in class on Tuesday, right? We said, well, here's how we relate. We take our tree. I won't be able to draw exactly that tree I had then. I'll draw a different one. Here's a tree with vertices, right? That's V plus 1 vertices. We're going to say this tree with V plus 1 vertices is a tree with V vertices plus another thing. So I'm going to take one edge here, this edge, and I'm going to draw the same tree, hopefully. Right? I'm going to say it's this tree, right? Which is the original tree except for this one edge with a vertex. And I'm going to say this has V vertices, right? plus it has this additional edge here. So my induction proof will be based on the fact that if I have a tree with v plus 1 vertices, I want to apply the induction premise for a subtree of it, the one with only v vertices, and then make somehow use of this additional thing that's happening. So I go back to my statements here. I have to obtain this t prime. T prime is just the original tree minus one leaf. Right? That's what I did. I erased one leaf. The degree of this vertex is this vertex right here. 1. So that's why it's a leaf, because I have degree 1. So I erase one leaf, I get a tree with v vertices, and I have this additional branch on top of that tree. If this works, if I apply the premise, induction premise here, because this has v vertices, I get from induction premise that the number of edges must be. What is this statement telling me? V minus 1 edges. But I have plus additional edge, this additional thing that's to go from this tree to this tree, I have to have this additional edge. I'm going to say plus 1, the edge that got deleted. So from here I get, okay, then my original tree of v vertices has v plus 1 prime. V edges. The discussion we left of this problem last time was how exactly can you control this procedure? The induction application here and then the addition of plus 1, that's easy. The part is, are you sure you can get from this tree to a tree of v vertices? What's the question?
So we just have to prove that every graph has these, for every tree has these.
Right. So to get this procedure to work, I have to remove a leaf. I said this last time, you can't remove an arbitrary vertex. You can't just say, take my tree, remove a vertex, and I've got this tree. Because that won't be true. If I remove this vertex or this vertex, I'm not getting back a tree of v vertices. I have to remove a leaf. This is a critical part. Remove a leaf. So to remove a leaf, I have to first prove that there is a leaf. That's your point, right? How can I remove a leaf unless I know for sure there is one? Yes?
I was going to say something else.
Go ahead.
Is it easier to start with v vertices and then add a vertex on each?
It's the same problem.
But we don't have to worry about v's then.
Right, but you have to prove the next statement, the v plus 1 statement, for any tree. You're going to say, I start with a tree of size v, right?
Yeah.
And then I add a leaf to it. So now the property is going to be true for my new tree. But how do you know your new tree can be any tree? You just prove it for some trees. That's the ones that you can obtain from the old trees plus a leaf, right? What if he comes up with a tree that's not one of your trees? So effectively what we want to prove, that's a very subtle way to make mistakes on induction. You say, I start from the statement of v, and then I build it up, and what I obtain is one of these v plus 1 vertex trees, right? That's incorrect, because you want to prove it for every v plus 1 vertex trees. So the right place to start induction, it's from this side. Once you make this mental connection in your head, how the new one relates to the old one. In this case, how does it relate? It's one edge with a leaf extra. That's the relationship. You don't want to start from the old guy, from the old tree, like he proposed. I have a tree of size v, I can add something to it to get the next tree. Because that next tree, it's a particular tree. It's not any tree. What you want to do is to start with any tree of size v plus 1. Right? I want to make clear everybody follows me at this point. If I start with a size V and I add one leaf to it, I'm going to get the tree of size V plus 1. But maybe not necessarily the one I want. Because the property has to be true for any tree of size V plus 1. Instead, it's better to start with the object that's in the conclusion. Start with any tree of size V plus 1. That's the tree I need to prove something about. From here, get to do something to get a tree of the old style, the V vertices. Now, because that's a tree of V vertices, I can apply the induction premise to it, and I get what I want. Yes, that's a question? That's a subtle point, but you want to start from the conclusion. Even in the summations, when you say from Sn I get to Sn plus 1, you want to start with Sn plus 1 to say, okay, give me Sn plus 1, let me see what I can do with it. So the critical part is why this procedure works, why I have a leaf. And that's, I think we did in a homework or in a recitation or somewhere, there was a problem that stated any tree has at least a leaf, right? So then we can use that result to say there's always a leaf that you can remove. I want to do this in a different way, the same problem, but I'm going to do it with a different induction, okay? Here's the induction proof 2, or alternative. I can actually go from here, from this example. I want to relate statement of V plus 1, but not to statement of V. So I'm going to have here something. I want to get to V plus 1. So this is the same like in there. It's all trees of size V plus 1. In fact, I'm going to use this tree right here for illustration. But I'm not going to go from V to V plus 1. I'm going to get from somewhere else. So my plan to go from the old somewhere else to V plus 1 is not to remove a leaf. The procedure I have in mind for this transformation, how to get from the old stuff to the new stuff, is to remove any edge. An arbitrary edge. So imagine I take this tree, I don't want to draw it again, and I say, okay, if somebody removes an arbitrary edge, pick an edge to it. Let's say I pick this edge, right? What am I getting when I'm removing that edge? I'm getting something weird, right? Like that. This edge is removed, right? And then what else is in there? Something like this. So the procedure I have in mind for how to go from the stuff that I know, which I didn't put yet, I'm not sure from where to go, to the V plus 1, is not removing a leaf, because that leaf requires an additional result that there is a leaf, like we just said. So remove any edge. What is this? What can I prove about this? If I take, again, I start with any tree of size V plus 1, and I remove an edge, what am I getting? What is this? Yes?
You get two different trees.
I get two trees. Is that always true? Do I have to worry about these cases? I have any condition like in here. See, I couldn't remove any node. I had to remove a leaf to get my stuff to work. Can I just say remove any edge, you're going to get two trees? Is that correct?
No, because like if you remove the nodes sort of like in the middle, then you get like 3 trees, or you can have any number of trees, or any natural number of trees.
What you're saying, if I remove an edge like this one,
Or if you remove an edge, oh sorry.
I'm only removing the edge. I'm not removing any vertex.
Oh, I thought you were removing a vertex.
Remove edge, all vertices remain. Am I guaranteed to get two trees now? Yes.
You can, if you take one of the like one of the leaves, if you take that edge out, then you're going to be stuck with one tree.
I get this tree, but is this node single not a tree?
Oh, you keep the vertex.
I keep the vertices. I'm only removing one edge.
I think you did the drawing wrong.
The drawing is wrong.
I think you forgot a vertex.
No, that
No, it's good.
Huh?
You're good.
I think I have all vertices, right? Let's count them.
Except
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Oh, that's a dot. Oh, I thought that was a vertex.
The dot in the middle of
The
the
One,
dot in
two,
the middle of the edge on the
3,
right drawing looks like a
4,
vertex.
5, 6, right? 7, 8, 9, 10, 11, 12.
I thought the dot was a vertex.
That's fine. I mean, Friday afternoon, we all like, oh man, we got a long week. Me too, actually. But everybody's on the same page with me here. What happened? I got a tree of v plus 1 vertices. What I remove any edge. Can I guarantee I get back 2 trees? I don't have to worry. There's no precondition. There's 2 trees. Huh?
It's a bridge. We proved that if you remove a bridge,
Right, so I have 2 trees. I mean, you can go by the proof by saying there's no cycles, they have to be connected, blah, blah. I think we did this before. We get 2 trees. Now, can I apply my induction hypothesis? Can I say, okay, those 2 trees are smaller than the v plus 1, right? Obviously. So can I say, okay, I don't know how many vertices are here. Maybe this guy has m vertices. Because when you remove an arbitrary edge, we don't know how many vertices will be on one of the trees. But if this was an m, how many vertices are here? Remember, I kept all the vertices. I did not remove any vertex. This is v minus m vertices, right? So if I apply my induction hypothesis now, my premise, how many edges are in this side? The property is true for smaller trees, right? So this gotta be m vertices imply how many edges?
m minus 1.
V minus, m minus 1, sorry. M minus 1 edges. And if this guy has, this guy in here is this tree, right? How many edges are here? V minus 1, m minus 1 edges. Good. So can I go back to this tree and count its edges now? Yes.
Shouldn't the tree on the left have v plus 1 minus m edges? Oh wait, actually. Where is it? Yeah, where is it?
Friday afternoon. I know him. He knows what he's talking about.
Right. Shouldn't the tree on the left have v plus 1 minus m versus because we had no like yeah, so
I'm saying
I'm like
there's v vertices total here, right?
there's v plus 1 because we took a tree out of v plus 1.
V plus 1.
Yeah,
This one has v plus 1 minus m.
I meant like
Right? I think he's right about that. It's my Friday afternoon. Let's make sure everybody's on the same page here. I got 2 trees, but it's the same vertices like before. If this guy has some m vertices, I don't know who m is, this guy has to have the rest, which is v plus 1 minus m. But those 3 are smaller, so I'm trying to apply the induction premise on each one of them separately. So how many edges I get here? M minus 1, and how many edges I get here? V minus m. Because I apply the property. Now I go back to this tree and I say, let's count how many edges we have here. How many edges we have here? All the edges from that side, plus all the edges from this side, plus 1, the one that we erased. So if I go back here and say, original tree, edge count. It's this one, m minus 1 edges, plus, that's how many I have there, how many, v minus m, right? Plus 1, that's the delete one. How much again? V. Is that what I want to prove? That my original tree has v edges. How many people with me on this proof? The key is, what is the induction premise here? Now I go back to say, I have to write this induction step, right? I know I'm proving v plus 1. But what do I need in the induction premise? Right? Because induction goes from something to something, and we prove v plus 1, but to prove it, we needed the property for a tree of size m and a tree of size v plus 1 minus m. So what do I need in the premise? What is this? I need some statements. All of them are the same statement. Of 3 of size blank has so many edges. But which ones I need on this side to be able to make this proof? Let's give somebody else a chance. What kind of statement I need there? Can I just say from V go to V plus 1? Would that be okay? Why not? Because I didn't just use V, right? I used the property for a 3 of size M and for a 3 of size V plus 1 minus M. So I need M and I need a statement for V plus 1 minus M. Right? If I know those two, I come to that. However, I can't state the induction step this way because I don't know who M is until I remove an edge, right? I need to make an induction step that's going to work before I remove the edge, and I cannot know M before I remove the edge. So I'm kind of stuck in here, right? What do I need to put on the left side to make sure this proof is going to work, whatever edge I remove? Without thinking I need to remove a certain kind of edge. I want the ability to remove any edge I want in here. And that's why I need certain statements on the left side. Yes?
But you like the statement of 1, 2, and then I got all the way to 3.
How about you saying put all of them, right? 1, 2, statement of 3, up to which one? V. Right? Would my proof work now? I say, I'm going to use all of them. I need all of them in my induction premise. Why do I need all of them? Because when I remove an edge, I'm going to get 2 trees of size M and size V plus 1 minus M. I don't know what those sizes are, but can I at least guarantee that those sizes are somewhere in here? Can I say both M and V plus 1 minus M, those two sizes, are on the left side, so I can apply the property on each one of them? So what I need is to say M is between 1 and V plus 1 minus M, the other size, it's also between 1 and V. Is that true? Anyway, you remove an edge, you get the 2 trees with sizes between 1 and V? Yes.
Can you explain why you need all the cases?
What?
Why you need all the cases?
That's what I'm just explaining here. I don't know who those sizes are, M and V plus 1 minus M, right? Could be any one of these sizes.
Right.
But are they for sure in this range? Is it possible to get sizes that are not in here? Can you get the 3 of size 0 when I remove an edge? No. Can I get the 3 of size bigger than V when I remove an edge? No. Again, what I do, I remove an edge on this tree, I get 2 trees. Can I guarantee that the 2 trees have sizes between 1 and V? I think I can. But I don't know which one. That's why I need all statements. Because I'm not sure which one of them I'm going to use. Maybe when he removes an edge, he gets a 3 of size 2 and 1 of V plus 1 minus 2. But when I remove an edge, I get a 1 of size 10 and V plus 1 minus 10. So I'm not sure which statements I'm going to need. That's why I need all of them in here. Hands up who's with me. Good. How do we call this induction step? Not the one that's N to N plus 1 or V to V plus 1, but one that says you need all of them to do the next one.
Strong.
So when you say weak induction is from Friday to Saturday, from N to N plus 1. When you say weak, strong induction is from all of them from before to the next one. Weak is just one step forward. Sometimes, in order to figure out what you need, it's good to do a little bit of prep work like me in here. I know if I remove an edge, I get 2 trees. And I'm looking at those trees and I'm saying, I don't know what sizes they're going to have. This is not a weak induction problem. Because by not knowing the sizes, I need more statements. V alone, just V to V plus 1 is not enough. So sometimes this procedure, this relation, how a tree relates to the old tree, in this case, dictates what induction you're going to need. This problem can be solved with weak induction, how we did it on Tuesday. But for that, we need a procedure specifically that removes leaf. If we want to use it this way, remove any edge, that's a different procedure, different relation between the new tree and the old trees. We're going to need in the induction step all the statements. Okay? So I think everybody can see how the calculation goes after that. If I remove an edge and I apply the statement, I get edges here plus the deleted edge is the right count. Oh, by the way, we need to do this. All right. So here's other examples of things like that. Any n cents with n at least 12, I think, can be made with coins of cents for 4, and 5 cents. So in other words, if you want to give n cents, you can write it as some amount of 4s plus some amount of 5s. It is A is the number of 4 coins, 4 cents coin, and B is the number of 5 cents coins. And doesn't ask for any n, just n bigger than 12. This is a simple problem, of course. I'm going to prove it by induction, of course. And I'm having this, if I want to do a statement of what is going to imply the statement of n plus 1. That's my induction statement. But I don't know yet what to put here. So this is going to say, if you can give change for that many cents, then you can give change for n plus 1. Right? That's what I want to do. So n could be 12, 13, 14, anything bigger than 12. So I'm looking at this and I say, how can I get change for n plus 1? Related to something from before. If you have this problem, give change to, say, 20 cents. How would you do it?
If the change of n had a 4 in it, you can take out the 4 point and add in 5 points.
The n plus 1 I have here.
Yeah.
So I think you can do it through n the way you say, but I want to keep n plus 1 as the conclusion in general to not confuse anybody. So what he's saying is, though your strategy for giving n plus 1 change in cents should be to subtract 4 or 5 out of it, right? And then give the change for the remaining ones, and then put that coin back, right? So this will be one coin, that is, say, 4 cents, plus the way to give change for the remaining, which is n plus 1 minus 4, right? Is that what you're saying?
Yeah.
If I know how to give change for the remaining n plus 1 minus 4 cents, I do that, and then I add one more coin of 4 cents to it to get n plus 1. Or I could have said, or I get one coin of 5 cents plus the way to give change to n plus 1 minus 5. Either one would be a valid way to give change to this number of cents. Everybody's follow me in the pattern here. N plus 1 is the amount of cents I need to give change. My coins are 4 cents and 5 cents. And I have an infinite number of coins. And then if I can take 4 or 5 out and give change for that amount, all I have to do is add one more coin, and I have my problem solved. Right? Is this a weak induction problem? Is it going from n to n plus 1? Or not? It's not a weak induction because it's not going from n to n plus 1. So it's going from where? From n plus 1 minus 4 or statement of n plus 1 minus 5. One of these will do my statement, right? If I know how to give change for one of those, then I can do that one. I think everybody can agree with this proof. The proof is very simple, right? If I give change for that, I add one more coin with 4 or 5. I have an infinite amount of coins, so it's not a problem of running out of coins, right? And I get done. The question is, how far back can this go, right? So, okay, for n plus 1, go to minus 4 or minus 5, and then go back. At what point this dies? Like, I can't go back anymore. Like, this is true if n plus 1 is at least what? It doesn't work for n equal 2, because for n equal 2, n plus 1 is 3, and if I subtract 4 or 5, I get minus something. That's impossible to give that sort of change, right? So while the induction step is very simple here, when we put it back the big picture, we have to check, okay, at what point this still works, right? So how this looks like? Statement of what is the smallest amount I can do with 4s and 5? I can do 4, right? Obviously. That's one coin. And from 4 I can do 8 and I can do 9, right? And from 8 I can do 12 and 13, and from 9 I can do 13 again. Maybe you just need one 13 here. And what else? 14. Okay, let's leave that there for a while. How about if I start with a coin of 5? Right? This obviously can do 5. And then what else can I do? I can do 9. And then I can do 10. And from 10 I can do 14, 15. So is it possible to give 7 cents with those coins, 4 and 5? How about 6? Am I missing? How about 11? So why it's not possible to give this change? It doesn't appear in my drawing here, right? These implications that I just proved with the induction step are these arrows, right? From 4 you go to 8. From 4 you can go to 9. From 9 you can go to 13 or 14. From 10 you can go to 14 or 15, so on and so forth. All of these arrows are built into this statement here that says you can get to any quantity if you can do minus 4 or minus 5. And I just draw these implications with the arrows. So every arrow is one of these implications. But now I need to look at what are my base cases here, right? I want to make everything bigger than 12 possible. So what base cases I need to prove this? Yes?
Well, you just proved that statement 4 and 5 eventually or indirectly will imply 12, 13, 14, and 15. And then 12, 13, 14, and 15, if you add 4 to all those numbers, like you'll get every number after that.
Right.
Consecutive.
So I need, according to his argument, I need one more step here. From once I have 12, 13, 14, and 15, once I have those done, I can get anything, any n further than at least 16, right? That's what you're saying, right? From 12, 13, 14, and 15, I can go everywhere further. The reason is, if I get any n bigger or equal to 16, n minus 4 is already done, because n minus 4 will be those things, right? So what base cases I need here to guarantee that this process will move on forever, right? Remember, I have to prove some. I think it depends on how you look at this tree, yes?
I was gonna say 12, 13, 14.
I agree. The easiest way to think about this problem is to do 12, 13, 14, and 15, and that's implying in his reasoning too. Once you have this, everything else moves. How about, can I make an additional argument to say I only need 4 and 5 base cases? If I say that, that's correct, but I have to do this manually. I have to say, okay, 4 and 5 are best cases. My implication here works from 4 and 5, it gets to 8, 9, 10, but it skips 6 and 7 and 11, right? And I can check that manually that this is the case. But I think the easiest way to do it is to say, look, after 12, everything will work fine, but you need 4 base cases if you don't want to deal with this part of the implication drawing. So how do we do 12 then? We need to prove those manually, right? How? 4 plus 4, or 3, 4a, you said? 3 times 4. So that's, let's just do 4 plus 4 plus 4. How about 13? 4 plus 4 plus 5. How about 14? 4 plus 5 plus 5. And 15? So we checked all those cases. Therefore, from here, we can go anywhere forward. Is this a weak induction? No, because it's not n to n plus 1. This is n goes to either n plus 4 or n plus 5. This is effectively the induction step. From any number of cents that you know how to do, you can do that plus 4 and that plus 5, but not n plus 1. That's why this is a strong induction. And we need 4 base cases to make sure that whenever we go back, we reach one of those. All right. So we have that. Here's another example. It's actually called Fundamental Theorem of Arithmetics about prime decomposition. Every number n bigger than 2 is a unique decomposition of prime numbers. Let's call E from exponent. E1, E2, E3, Pk times Pk. So these Pi's are prime numbers, and Ei's are all bigger than 1 integers. So every number can be decomposed into primes. We can prove this by induction. But we're going to need strong induction. We're going to say, assume statement is true for 1, 2, 3, all the numbers to n. So that I'm assuming I already know it for all of them. That the statement of 1, statement of true, you know, all of them are true, and I'm going to prove the statement for n plus 1. Meaning, if what I'm saying here on the left side in the premise, I'm saying if for any m that is between 1 and n, I know that m is a decomposition of primes, then I can prove the same. N plus 1 is decomposed into primes. how do I prove this induction step? This is a strong induction. Because again, I'm needing not just n to n plus 1. I'm going to use that all the numbers before n or up to n are decomposable into primes. So how do I prove this? I say, okay, remember in induction proof, I start from the conclusion. I have to somehow relate this number n plus 1. How do I relate this number to the previous stuff? Yes?
So it's either something in that list times something else in that list?
So it's either some A times B, right? A product with A and B
Smaller.
between 1 and n, or
Or it's its own prime.
it's a prime number. That's what he's saying. Any number n plus 1 or any other number, it's either a factor of number smaller than it. I should say starting from 2, right? Because if one factor will be 1, the other one will have to be n plus 1. So it's either a product of factors, not 1 times itself, or it's a prime number, by definition, right? If it's not a product of numbers, it's got to be a prime. If it's a prime, then how do I write this prime in that form? It's prime, that prime at power 1, right? So if it's a prime, it's of this form. It's just that prime at power 1. So that's done. What if it's AB? If it's a product of these numbers, what do I need to do now?
Decomposition.
I apply the induction
Yeah,
premise. I say those A and B's are in this list somewhere. So now I use the fact that for numbers n or lower, I already know they have a prime decomposition. So I say, okay, who's A? A gotta be some E1, E2, EK, that's A. And B has to be some numbers, P1, so see, other primes. Q1 at F1 times Q2 at F2 times QL at FL. So that is A decomposed A into primes. And this is B into primes. This is the induction premise. It's saying that for numbers that are smaller than n plus 1, up to n, I already know they can be decomposed into primes. So now, is this a prime decomposition here? If I do the multiplication and I add the exponents, if P2 could be the same as Q1, right? This prime factor can be the same as that prime. What do I have to do? I add the exponents, those two, and I get the exponent of that factor in here, right? So by doing the multiplication, I get all primes at some exponents. Would that be a valid decomposition for my new number? That's n plus 1. Hands up, who's with me? Good. So what did I prove? If this is true for any number up to n, it's also going to be true for n plus 1. I have a question here for the honor section. This is regular stuff. I'm going to add something to the theorem that's not that easy to prove, but maybe one of you can do it. This decomposition is true. Every number can be decomposed into that, but it's unique. Like every number has decomposition. That's the easy stuff we just proved. The second part is the decomposition is unique. You can't get a number to decompose into primes in 2 different ways. It's true that it always decomposes into prime, but that decomposition is nailed down to be exactly 1. Apart from changing the order of the primes in the multiplications. 2 at the power 5 times 3 at the power 4, it's 3 at 4 times power 5, right? Apart from that particular rotating the factors here, the decomposition is unique. That's a little tricky. So it's an exercise for you guys. We'll see. When we get to number theory, we're going to get back to this problem, but maybe by then somebody can prove this. Back to the problem of there is a decomposition. This is a strong induction. It's not going from n to n plus 1. Right? It's going from everything up to n into n plus 1. Okay. I want to do maybe one or two more examples here to get you familiar with more induction problems. Oh, by the way, I have also another questions for this problem. Too bad that I deleted the 3, but the 3 is not needed for what I want to answer. So honors exercise. What this theorem is saying, in effect, you guys remember handshaking lemma? Yeah, make sure you remember it for the midterm, right? 'Cause it's going to happen in the midterm, that one. So what this is saying, it's saying that effectively the theorem says the sum of the degrees in here is how much? Instead of saying I have v minus 1 edges, I can state the same exact thing with the sum of the degrees, right? Because for any graph, the sum of the degrees is exactly twice the number of edges. So I could state this fact by saying sum of the degrees has to be 2 times v minus 1, right? So this theorem in effect is saying if you have a tree with v vertices, the sum of the degrees, it's guaranteed to be 2 times v minus 1. Your job is to prove it the other way. If there is some integer values, x1, x2, up to xv, with the property that the sum of xi is 2 to the v minus 1, and every xi is at least 1, those are the degrees. There's some integer numbers that they all bigger than 1, and they sum to 2 times v minus 1. Prove that there is a tree with degrees x1, x2, up to xv. So it's the statement, just backwards. If there is a tree with vertices, the sum of its degrees is 2 times v minus 1. Now I want to prove the opposite. If somebody gives me a bunch of numbers, those degrees that sum to 2 times v minus 1, I can construct a tree that has exactly those degrees. That's not hard. It's another induction exercise. It's a weak induction. Just prove it from v goes to v plus 1. If that statement is true for v, why is it all true for v plus 1? So this is induction from v goes to v plus 1. So you have to think, how do I build a tree with those vertices, assuming I can do this tree for v minus 1? If somebody knows how to do it for v minus 1, then I can do it for v. Question?
This can be done about the topic. Like, so the difference between a weak and a strong induction is like weak you prove from n to n plus 1, and strong is you prove for all n to n plus 1.
Yes, that is true, but in practice we don't need all n. We say from all n, but in reality we might use only 2 or 3 of them. Anything that's not simply n to n plus 1 is strong induction. Whether you actually use all of them, or you use maybe n and n minus 2 and n minus 5, maybe, it's still strong induction.
What were the base cases for the minus 1v?
Right, good question. We skip the base cases. For this property to work, how did it work from where to where we prove it? So when we say from all of them to stay to n plus 1, I got it from 2 to 3. Did I prove that? I guess it was 1 and 2 to 3, right? What else did I do? 1, 2, 3 goes to 4. Did I do that? From everything up to 3, I go to n plus 1. So if you put n equal 3 in here, I get from 1 to 3, I can go to 4, right? And from 1, 2, 3, 4, I can go to 5. So 1 is not interesting to me because it's not included in the statement. So what's the best case that it's not proven? It's not proven from the left to right. What is not implied from before? Base case n equal 2. Now 2 is a prime, right? So I don't have to worry about it. 3 is its own, 2 is its own decomposition into primes. But that's the only thing that's not proven by induction. the case 2. The other cases are all proven from 1 to 3n to n plus 1. Okay? So before I do what I want to do here, I want to prove one more thing. Oh, by the way, that recitation from this week that I thought is quite hard, I keep saying it's difficult, 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 right? Remember that? Some people apparently solved the whole thing last night. Not the whole thing, but at least 2 or 3 people were just running through all those problems and solved them, like almost all of them. Maybe it's not that hard, but that's my conclusion after last night. But we did find one that I thought I have the solution, but it turns out I don't. So there's one with some hemispheres that I still don't know how to do. How about binomial theorem? What does it say? X plus y at n is the sum from k equals 0 to n choose k, x to the k, y to the n minus k. Of course, I want to do it by induction. So I'm going to go from n to n plus 1. That's weak induction. How is this statement, induction step, going to look? From n, how do I go to n plus 1? What would be the equation for n plus 1? Equal with what? What do I write?
K equal 1.
0.
Oh, yeah,
Two.
2. N plus 1. N plus 1 choose K. Pi is X. Choose the K. Times Y to the N plus 1 minus N.
Right? That's the same. If the binomial theorem is true for the exponent n, it's also true for n plus 1. So induction by n. Don't get confused with this k. K is an internal iterator that depends on n. It runs from 0 to n. The induction statement is on n. This at power 2 means something, at power 3 means something else. That's the induction statement. This is a weak induction because it's just from n to n plus 1, right? So how do I prove this? Like in any induction step proof, where do I start? In conclusion. I'm saying, okay, that's my new customer here. How do I deal with this customer? I have to deal somehow with this in relation to the old customer. What's the relationship between this customer and the old customer? Right? What's that relationship? This is something you have to think before you even write it down. Mentally speaking, conceptually, how do I relate that guy to this guy? It is a common sense English question. It's not about induction. It's how do I handle this with respect to that? It's just that times what? Right. So then that's where I start. X plus y at n plus 1. It's got to be x plus y at n times x plus y. That's the relationship between them. So now what do I do? I apply the induction premise here, right? The whole point of stating it that way is that this is the premise, so I know this stuff. And that's the conclusion. So, of course, I can replace x plus y to the n with what I know. So let's do that. I'm going to move this x plus y in the front here, times sum from k equals 0 to n, from n choose k, x to the k, y to the n minus k. And now I'm going to open parentheses. I'm going to say it's x times this guy plus y times this guy. So this is x times this sum. Plus y times this sum. That's easy, because it's whatever the sum is times x and times y. Now, I'm going to bring this, the sum that I really want first in my paper here is the one with the x to the k. So I think it's this one. I'm going to reverse them a little bit. So this is a sum, n choose k. K goes from 0 to n. N choose k, x to the k, y to the n minus k plus 1. So this is this sum here. I'm going to put a circle to it, and the circle here to be clear which one is it.
Should be a y.
Right, I move the y inside.
Oh,
What happened is y to the power 1, I multiply with y to the n minus k, so the exponent now is y to the n minus k plus 1. Now I'm going to do the same for the x sum. I'm going to say sum from k equals 0 to n of n choose k. X is at what power now? K plus 1. Y at n minus k. All right? So then, what I want to do, for now I'm going to keep this one in place. Just I'm going to say n plus 1 minus k. Instead of saying n minus k plus 1, it's a plus 1 minus k. But this one, I'm going to iterate it. I'm going to keep the sum as it is. Just instead of counting from 0 to n, I want to count this sum from 1 to n plus 1. This is a trick that maybe you're seeing now for the first time, maybe not. Is a change of variable or change of indexing without changing the actual content of the sum. So I got to be very carefully how I write this stuff. This in here is not n choose k anymore. It was n choose k for values 0, 1, 2, 3 up to n. But now the same values in terms of the new variable I have, k, what do I have to put here to make the same values like before, just indexed by a different k? What was the first value? N choose 0. The second one was? And the last one was n choose? So I want the same here. I want the first one to be n choose 0, but I don't have 0. I have the first one is 1. How do I write 0 here? K minus 1. In integrals, this happens all the time when they do integral. They leave the integral alone, just change the variable of the integral. So then x is at what power now? K minus 1. And y is at what power?
N minus k.
Isn't x at k?
N k plus 1.
K plus 1. So that's at k then, right? Because what's at k? This is k plus 1? Oh, I see. Is this one from here, right?
Yeah.
And then how about the y?
N minus k minus 1.
It's n plus 1 minus k?
Minus k minus 1 becomes minus k plus 1.
Right? So it's let's write it the way you say it makes more sense. N minus k minus 1, right? Okay. So now this k plus 1 is in fact k minus 1 plus 1 now. Can I make it more clear? Because my variable k becomes k minus 1 because I index the sum from 1 to n plus 1 instead of 0 to n. Now I want to break this up a little bit. I want to take a factor out here. I want to take the 0 factor out. So this is y to the n plus 1. Plus the rest of the sum is from 1 to n of n choose k, x to the k, y to the n plus 1 minus k. So only thing I did, I took the k equals 0 as a separate term. K equals 0 produces y to the n plus 1, right? So that y to the n plus 1 is the front. The rest of the sum is from 1 to n. In here, in the other sum, I'm going to do the k from 1 to n separately. So that's n choose k minus 1, x to the k, y to n minus, what we say this is? N plus 1 minus k. And the term that I don't have here is who? What term did I skip in there? N plus 1. The last term. So the last term is what? If I put k equal n plus 1, what do I get?
N plus 1.
X to the n plus 1. Now I look at these two sums and say, hey, they're very similar. They have all from k equal 1 to n, k equal 1 to n. They have the same exact polynomial terms, x to the power k, n to n plus 1 minus k, x to the power k, y to the n plus 1 minus k. The only thing they have difference is what?
Coefficients.
The coefficient. So I'm going to group this into one sum, y to the n plus 1, plus the sum from k equal 1 to n. Here's the two coefficients, n choose k plus n choose k minus 1 times xk y to the n plus 1 minus k. I group the two sums into one sum because they have this common factor, right? And the only thing I have to add is this binomial coefficient plus this binomial coefficient, right? If I add those two together, I get this parenthesis here. Hands up who's with me. Okay? Any questions? Like in what step are we stuck from where to where? And I still have the x at n plus 1. Now, who is this? Remember the Pascal formula?
N plus 1.
This here is who? N plus 1
Choose k.
choose k. So this is y to the n plus 1 plus the sum from k equal 1 to n of n plus 1 choose k, x to the k, y to the n plus 1 minus k, plus x to the n plus 1. But these two terms are exactly the same term like in the sum. For k equals 0, I get this one. And for k equal n plus 1, I get this one. So I have this sum here. It's from 1 to n. I can add two terms to it, the 0 and the n plus 1. Again, for 0, if I put k equals 0, I would get y n plus 1. So this is just n plus 1 choose k, x to the k, y to the n plus 1 minus k. The two terms additional are exactly x n plus 1 and y n plus 1. So, done. That is exactly the formula for n plus 1. I use this trick with the binomial thingy, right? That these two coefficients, I have to manipulate. Now, conceptually, what happens here, I manipulated these sums down to this point where I could do the common factor and add them up. I need this expression to be the same like this expression, so that when I do the common factor, I get the sum of two binomial coefficients that are consecutive, k and k minus 1. And now using the Pascal triangle, I get that that's the new coefficient, that's the one I want in my final sum. And I'm done. Of course, I do a lot of scrapping to make this work at home, right? I mean, it's not like I came up with it right here in class. It's a lot of back and forth to do the sums right and wrong until you make them work. But that's how mathematics works, okay? It's not, I'm not trying to say, wow, when am I going to be able to do this by myself? Well, it's a lot of trial and error before you get it done, but combinatorics is a lot of these summations. So I think you have to take a look at this step by step again at home. How does it go from there to there? How does it go from there to there? So on and so forth. But also, what concept drives this theorem, this derivation? Like my main central point was to get from here to here. I knew if I get to add those two together, I'm going to get the binomial coefficient that I need. So I try to get to this point so I can add them up that way. All right. The one thing that we need to do next, also about strong induction. This is weak induction. But here's one that I'm going to do now. Very important topic in both mathematics and computer science is the Fibonacci numbers. And there is plenty more induction problems that are stated on the website and in your recitation paper. Make sure you do as many as you can before the quiz. Quiz won't have complicated stuff like the binomial theorem, so make sure you are very fluent in the simple stuff, induction problems. The principle of Fibonacci numbers is very simple. You add the last two to get the next one. So where is this going? If I add the last two to get the next one, how much is F2?
1.
Adding the last two. 30. So how do I write this relationship in general form? Fn plus 1 or Fn is Fn minus 1 plus Fn minus 2, right? The last two. If n is at least 2, right? And if not, it's 0. Like if n is smaller than 2, I get f0 equals 0 and f1 equal 1. That's like base cases, definition. This relationship, fn equals fn minus 1 plus fn minus 2, is a recurrence. This particular recurrence is very important mathematics, but you're going to have to deal a lot with recurrences in general, because a lot of algorithms running time are recurrent formulas. You're going to see things like Tn is Tn by 2 times 2 plus n, for example. That's a recurrence that says the running time when you sort n objects is twice the running time for sorting n by 2 objects plus a linear time. This in here is the running time for merge sort, for example. And you're going to have to know how to solve recurrences, because most algorithms are divide and conquer problems, break into smaller problems, solve the smaller problems, put it back together. They're natural recurrent things because they solve the smaller problems. That's it. Merge sort, to solve the problem, you need to solve 2 subproblems of size a half and then put it back together. So be ready for recurrences because they're going to come big time. This is one example, but you're going to have a lot of recurrences. So I want to solve these if I can. Recurrences are defined sometimes that way, but they have a closed form solution. Like I can tell what the Fibonacci numbers are. So my main question for today is, what is Fn in closed form? Is there a formula for this? Not recurrent, not depending on the previous 2 ones, but just a general formula for Fibonacci numbers. Right? So how do we do that? If I am to ask you this, how would you approach this problem? Other than Googling it and see what is it. If a problem, this is the problem you're going to have in recurrences. You get the recurrence from the algorithm form, but then when you have to solve it, you have to figure out what kind of function that is. So here's a way I can think about it. I say 2 to the n plus 1 is 2 to the n plus 2 to the n. Right? That sounds to me almost like Fibonacci. This Fibonacci of n plus 1 is fn plus fn minus 1. So the only difference is this, if you look at those two things, 2 to the n, f to the n seems to be the same kind of indexing, but this one is not adding fn, it's adding the previous guy. So just for the sake of the argument, if I say the recurrence is gn plus 1 is gn plus gn, g is not f, it's a different sequence. What would G be? Be 2 to the n, right? Because what numbers is double the previous one? What kind of sequence? This is 2gn, right? If I have a sequence that says double the previous guy, that sequence, it's essentially 2 to the n, maybe times the original initial offset, right? Maybe times the constant. You can think about this in terms of geometric progressions. If the next guy is twice the old guy, you're gonna get a geometric progression. Or if the next guy is 3 times the old guy, it's always a geometric progression. So my analogy is, this is true for 2 to the n, but it's not true for Fibonacci. Although Fibonacci has the same sort of pattern in my head. It's like, instead of gn plus gn is fn plus fn minus 1. Just a little bit off. So my conclusion from here is, what can I tell between f and g, or f and 2? Which one grows faster? 2 adds the previous one twice, or doubles the previous one. F is the previous one plus not the previous one, but the one before it. Should f be smaller than 2 to the n or bigger? But on the other hand, this to me, I'm going to say something very non-mathematical, looks exponential. As in, okay, it's more than 2 to the n, but it seems to me like it grows almost like an exponential. Perhaps it's 1.8 to the n, or 1.6 to the n. It has to be lower than 2 to the n, but it sounds to me like it's bigger than, say, n squared or n cubed or something like that. So I'm going to make a guess that says, I believe fn is roughly some exponential my guess is that x is between 1.5 and 2. The base of that exponential is it's something lower than 2, but not too low. That's just a guess, okay? I don't know if it's true. I'm just saying, looks exponential, and I know for sure it's more than 2 to the n. Okay, so I'm gonna try to keep going with my guess here. If that's my guess for this recurrence, I'm gonna say, well, let's play it out. How do I write this formula then if this is an exponential? Who is fn plus 1? If my guess is correct. And who is then fn? X to the n, right? Plus x n to the minus 1. Well, I maybe not equal, maybe it's approximative, maybe because I'm just guessing around here, right? Can I solve this equation? This has to be true for any n bigger than 2, right? I can divide by x at n minus 1 and get what? If I divide everybody by x at n minus 1, what do I get? X. If I take out n minus 1 x's, what am I left with? X plus 1. Okay. Or I can write this equation, x squared minus x minus 1 is 0. Now I can solve, this is a quadratic equation, right? I can solve it. So it has 2 solutions. I'm going to call one of them, I mean, I can even draw the little plot here that says this is 1/2. This is a parabola with the center here. This is x squared minus x minus 1 function. And then it intersects. This is the solutions. I'm going to call this one phi, That's a standard notation in mathematics, is phi, Greek letter. And this is called phi complement in a quadratic sense, so it's phi bar. Phi turns out to be, how much is it? 1 plus square root of 5? I have it here somewhere.
1 plus root 5.
And phi bar is 1 minus square root of 5. So far I have a guess. I'm saying this is kind of the generator root for Fibonacci numbers in terms of the growth. The actual formula is P at n minus P bar at n divided by P minus P bar. So that is 1 plus square root of 5 by 2 minus 1 minus square root of 5 2. And the difference between these two guys, phi minus phi bar, is 1 plus square root of 5 minus 1 plus square root of 5 divided by 2, that is square root of 5. My guess is correct, but not exact. Here's why that is. It's not exact because it's not exactly phi to the n, or this root, right? My solution will be this phi, and then it's not exactly x to the n. That's why it's approximative. But why asymptotically, when n grows, this is approximatively just this, 1 plus square root of 5 to the by 2 to the n. Is because this stuff in here at the big power becomes insignificant. If you do the calculation, 1 minus square root of 5 by 2, it's a number that's between 0 and minus 1. So when I raise it as a big power, this whole thing becomes irrelevant in terms of size. It's not 0, but it's a number that's very close to 0. So then, what I want to do is to try to prove this by induction. Before we do so, we need some equations. So we have phi squared plus phi plus phi squared minus phi minus 1 is 0. That means phi squared is equal to 3 plus 1. This number is called the golden ratio. And we have phi minus 1 equals 1 over 2. So now, we want to prove this formula. Phi at n minus phi bar at n over 3 minus phi bar by induction. So now, how do I write an induction step here? I want to get phi of fn plus 1. So that, according to this formula, is going to be phi n plus 1 minus phi bar at n plus 1, phi minus phi bar. But what statements am I going to need in the induction premise? That's the conclusion. And this is the premise. So what do I need to put in my premise to get fn plus 1? which previous statements? Is it going to be from n to n plus 1?
Yeah.
Can I just say if Fn is phi at n minus phi bar at n over phi minus phi bar, therefore Fn plus 1 is that? Would that be enough? How, if I go a little bit into the proof, how can I relate Fn plus 1 to the previous all guys?
Would it be Fn plus Fn minus 1?
It's going to be this one plus Fn minus 1, right? So what do I need in my induction premise here? Which statements I need? I need two things. I need Fn minus 1, phi at n minus 1, plus phi at n minus 1 divided by phi minus 1. So I need those two. It's a strong induction because it's not just going from n to n plus 1. The step goes from n and n minus 1 into n plus 1. If I know the formula for Fn and for Fn minus 1, then I can prove it for the next Fibonacci number. So of course, how do I relate the next Fibonacci number to the previous ones? It's the recurrence is given to me in the definition. So I'm going to say Fn plus 1 is Fn plus Fn minus 1. I apply the induction hypothesis in here. Phi n minus phi bar n phi minus phi bar plus phi at n minus 1 minus phi bar at n minus 1 divided by phi minus 1. Now it's the ball game where here's the ball, here's what I'm trying to score it. This versus this. This is my ball, this is what I'm trying to go with it. What do I see? First thing, I notice the denominators are exactly right? So I'm trying to add those two things and get to this. So I can easily do that. The denominator is done. I'm going to get phi n plus phi n minus 1 minus phi bar at n minus phi bar at n minus 1. So don't get confused with this bar. That's not a minus sign. That's a phi bar. This bar is the complement of phi. Sometimes it's called xi. If you prefer writing it that way, you're going to see some mathematics wrote this way. I just prefer to have just one symbol. But then this bar in here on top of phi is not minus. It's just the bar, as in complement. Hands up who's with me so far. Good. So the denominator is done. I can take my eyes off it. Now, how do you think I'm going to get this and that? Like, I think those two together, it's got to be this. And those two together, got to be that. Is that true? If I add those two, I get this? This is the equation that we're going to need here. Because phi is the solution to this equation, we need to use this fact that phi squared is phi plus 1. So I'm going to do a common factor, phi at n minus 1, common factor. What is remaining of those two if I do phi at power n minus 1? What's remaining from here? Phi plus 1. And the other one the same. This is phi bar at n minus 1. What's remaining of them? Phi bar, because this is a different one. Plus 1 or minus 1? I think plus 1. Because the minus is in front of it. Right? Phi minus phi bar. So now I can extract from here which one is phi plus 1 from this equation. It's phi squared, right? 1 plus phi is phi squared. And the same happening for the other guy. The other root has the same exact property. Phi bar squared is phi bar plus 1. Therefore, the same thing happens. So this is going to be phi at n minus 1. This phi plus 1 is phi squared minus phi bar at n minus 1 times phi bar squared divided by phi minus phi bar. So now how much is phi minus 1 times phi squared?
n plus 1.
Phi to the n plus 1 minus phi bar at n plus 1 divided by phi minus phi bar. Jackpot? That's it, done. That's the induction step. I just proved that this formula is true for n and n minus 1 is true for n. So back to the induction tree drawing. What did I prove? From 0 and 1, I go to where? This is different than the tree. It's not an or. It requires both of them, right? From 0 and 1, I get to 2 maybe. Right? From f0 and 1, I get. I don't mean the value. I mean the actual f index. From 1 and 2, I go to 3. From 2 and 3, I go to 4. From 3 and 4, I go to 5. So which ones are my base cases? What is not being proven from something else?
0 and 1 and 1 and 2.
F0, let's see, what is F0? 0. And what is this formula? It's phi at 0 minus phi bar at 0 divided by phi minus phi bar. True or false? Is that 0?
Yep.
How much is phi at 0?
1.
Phi bar at 0?
1.
How about phi 1? How much is it? It's 1, the value. And this is phi minus phi bar divided by at power 1 minus phi bar. So phi minus phi bar divided by itself is
1.
checks. So I got the base cases. And I like the base cases at the end, especially because after the induction step, I like to think that way. What did I just prove? I can get 2 from this, I can get 3, I can get 4, I can get 5, I can get whatever. I look at this and say, which cases I'm not getting from the induction step? 0 and 1. These ones gotta be base cases. Everything that I'm not getting from the induction step has gotta be base cases. Now, this is a very powerful mechanic. If you know the closed form of a recurrence, it's just like the other sequences. Any calculation, anything anybody ever asks you about the sequence, if you know the closed form, immediately plug in the closed form. Sum the first n terms, product something, prove that the factorial divide, whatever. If you have the closed form of a sequence, the problems become much, much easier because you immediately replace f5 with the formula for 5. Phi at 5 minus phi bar at 5 divided by phi minus phi bar, in this case. Same thing with all the stuff we did last time or at recitations. If I know that's 2k plus 3, immediately in any calculation, any problem, any induction, anything, I plug in 2k plus 3 immediately. The difficulty is some of the sequences, it's hard to get the closed form. I asked a few people who came Tuesday at office hours, Fibonacci numbers, they struggled for an hour, they couldn't prove anything. Why? They didn't have the closed form. Right? If I say this is smaller than 2 to the n, now it's obvious, if I know the formula, I can prove immediately this is smaller than 2 to the n. In fact, I know asymptotically exact how much is it. It's 1.68 to the n with the closed form. If you could solve a recurrence in closed form, that's the way to do it. Sometimes it's difficult. So let's try to do some exercise here with Fibonacci numbers. I have something that says exercise. Fn plus 1 is phi times Fn plus phi bar at n. I don't know, is that true? I have another one. Maybe I shouldn't solve them. Maybe I should just leave you to solve them, all of them. How about phi to the n is fn times phi. This seems to be a common theme here. Plus fn minus 1. That'd be a great quiz question. I guess for the honor section, because the other regular sections, they don't get this whole derivation of Fibonacci. They just get the, it's fn plus fn minus 1, that's it. So if you just know the recurrence, this stuff can be quite tough. But if you know the closed form, I think it's easy. So here's another one. 3. Fn is the sum from k equals 0 to n minus 1 by 2. That seems complicated, right? Oh, look at that. That's a biggie. That's something with the Pascal triangle, right? These are binomial coefficients in here, right? Huh. That's an interesting one. Let me see, I have another one here. 4. F1 plus F2 plus Fn apparently is Fn plus 2 minus 1. Who would have guessed? Right? I mean, this got to be easy by induction, right? If this is true, well, how do we get an induction step out of here? Like F1 plus F2 plus Fn plus Fn plus 1 has got to be minus 1. Right? So that's an induction step. So how do we prove this step? Again, like with any induction step, we start from where? This is our new customer here. So this is an induction step. If this, then that. So how do I do this? F1 plus F2 plus Fn plus 1. I say, I already know this guy from the induction premise. So how much is this? Fn plus 2 minus 1 plus Fn plus 1. So how much is Fn plus 2 plus Fn plus 1? These two guys. According to the Fibonacci definition, there's two consecutive Fibonacci terms added up together. How much is it? Is the next one, right?
Yeah.
Done. That's easy. So I'm not going to prove those 3 then. I see, maybe you guys can do it. Some of them might be easier from the recurrence. See, this is easy without solving in closed form, right? I only need the recurrence equation to do this. But some of this stuff might be easier to do with the closed form of the Fibonacci numbers. So that's what I have for strong induction. Our plan is to focus first on quiz and the midterm. And then we'll focus on some more interesting induction problems that were in your recitation pack from this week. And I think we're going to have to do induction a little bit after the midterm to get ready for the next module. Now, one more thing. We are preparing some sort of review additional sessions for the final exam. Those are not honors reviews. So if it says midterm review Thursday, I think I'm scheduled to do it on Thursday evening. There won't be anything with honors. So if you need more practice for the midterm exercises, that's the one. If you expect to see more fancy polygons and red and blue dots and all that, that's not going to happen on the review sessions. Okay?
That proof actually makes sense. You always know that that's the only part that makes sense.
Sometimes you just that's how it goes with induction. You just need it.
You just gotta go with it.
Wait, yeah, I didn't
No, number three for sure.
I don't know what just happened. I accidentally disabled this morning, and I had two headphones. My body doesn't know what time it is. Such a disaster.
But he deals with all, it's not just you. There's like 25 people.
Hey, could you throw my sweatshirt at me, please? And anything else I might have left on the ground?
I think
Thanks, you're a G.
you know this or you found the answer?
I saw it years ago. I forget.
This is like, okay, you took a bunch of
I'm gonna stop the camera and
That's the kind of problems you'll find there. There's
Bunch of growth colors.